So next up is 4C, which is, as I told you before, the extension of predicon. The basic idea of predicon was that we learn some kind of distance measure, but in an axis parallel variance analysis, some new distance measure, and then integrate this distance measure into dbScan. And the same idea is followed by 4C. So to put it a little different, we extend a cluster from a seed, a core point, as long as the density criterion is fulfilled, like in DBS, but and otherwise we pick another seed unless all data objects are assigned to a cluster or noise. So this is the basic scheme of dbScan. And now the density criterion is a minimal required number of points in the neighborhood of a point, which is the same, but the neighborhood now will be will have a different shape, because we now want to have so in predicon we had this axis parallel ellipsoids, if you recall, and now we want to have an arbitrary oriented ellipsoid actually. So neighborhood is the distance between 2 points based on the eigensystem of both compared points. So instead of in predicon we used those axis parallel ellipsoids, and now we have an eigensystem that spans actually an ellipsoid. So what do? Well, we perform PCA on the local neighborhood of a point to find the subspace correlations, to find the correct eigensystem. In order to find the correct eigensystem, so recall we had this, so this is basically the same idea as predicon. So in predicon we did, we compute the epsilon neighborhood, then we did a variance analysis along each attribute, and those variances that have a smaller, those features that had a smaller variance than some given threshold, that were considered to be the interesting one, and the others are considered to be the non-interesting ones. And the same actually is now here, but now we don't have axis parallel variance analysis, but we have a covariance analysis with PCA. So we still need a threshold, which is delta, which discerns or differentiate between small and so strong and large eigenvalues actually. And we use the so-called correlation dimensionality of the neighborhood of a point as the number of eigenvalues that are smaller than this threshold. So the variance along those eigenvectors are greater than this threshold here. So those are the strong eigenvectors actually. And in the eigenvalue matrix of P, which is computed by PCA from the local neighborhood here, we simply replace the large eigenvalues by 1 and the small eigenvalues again by a value kappa, which is greater than 1. So this is exactly the same as we did in predicon, but the only difference is that again we don't look for axis parallel variance, but we look with PCA for non-axis parallel variances. And so we exchange or replace the corresponding eigenvalues as told before here, and the adopted eigenvalues matrix is now denoted as E prime of P. So each point gets its own E prime, because for each point we compute the neighborhood in the full dimensional space, do a PCA, and then replace the eigenvalues accordingly to this rule here, depending on delta. So the effect is similar to predicon. Now we have not these axis parallel ellipsoids, but we now have those non-axis parallel ellipsoids. So in the direction of high variance we have epsilon. So the epsilon neighborhood actually is now only in those directions with the strong eigenvalues, and in the direction of the small eigenvalues, of the weak eigenvalues, we have epsilon times kappa. So this is somehow bumped here. So this is actually really an ellipsoid. In the strong directions we have a weighting vector of 1, and in the small weak direction of weak eigenvalues we have a weighting of 1 times kappa, and kappa is greater than 1. Yeah? So once again, the distance is not symmetric. Because the distance now, if we use those E primes, those adopted eigenvalue matrices, we can use that as in the distance measure in the Mahalanobis distance. So if we do that, same story as in Predicon, we have the problem that this is very specific to P. Yeah. So the distance from P to Q is different than different than the distance from Q to P, depending on which E prime we use. If we use E prime of P or E prime of Q, they may be different. Yeah. So again, we need a symmetric distance measure in order to use dB_scan with this distance measure. And again, we use just the maximum of the two things. And we say that P and Q are correlation epsilon neighbors if the maximum of the two of their corresponding distances is smaller than epsilon. Yeah. So here you see an example where the 2 points P and Q, P is red, Q is blue here, and the corresponding epsilon neighborhood with their own E prime. And you see here that, maybe take this one here. So they have to find themselves in their own epsilon neighborhood, in the adopted epsilon neighborhood here. Yeah. So if they find themselves simultaneously, they are epsilon neighbors. Here only P finds Q, but Q doesn't find P in its own epsilon neighborhood. Yeah. So in that case, they are not epsilon neighbors because the maximum is greater than epsilon. The maximum would be corresponding to Q here with the E prime of Q. Yeah. So that's the basic idea. But once again, very similar to Predicon. The only difference is that we are now axis parallel. Yeah. So and then the algorithm works exactly like dB_scan. Using this formulation, or actually this distance function. Yeah, that's it. Yeah, so Predicon actually, 4C of course, finds arbitrary numbers of clusters like dB_scan. It requires the specification of the density threshold as dB_scan, which is min PDS and epsilon. So min PDS now reads mu here in 4C, but don't get confused. That's the min PDS parameter of dB_scan, the minimum number of points, and the radius of the epsilon neighborhood. So the epsilon is the radius of the neighborhood. And we need 2 additional parameters, the maximal dimensionality lambda of the correlation clusters. This is unfortunately required because otherwise 4C can also find, or tends again, like ORCLUS before, tends to find full dimensional clusters, and that's no distinction to dB_scan. So in that case, we can just run dB_scan with less overhead actually, because 4C always computes this PCA stuff on the local neighborhoods and stuff and so on and so on. Yeah. And the second parameter is the delta for the distinction between strong and weak eigenvectors. So this one here, yeah, like we had before in Predicon. Okay, and yeah, those 2 parameters actually are erased by some extensions. We mentioned CoPark that take the minimum number of strong eigenvectors that explain a fixed portion of the oval variance. So like we did that in PCA, we talked about that. So for example, we take the ones that explain 80% of the variance. Yeah, and we can of course do the same here. This actually does not get really rid of the delta parameter, but somehow hides that in an internal parameter. But still, this parameter, of course, could be set in CoPark. Yeah. So anyway, that's 4C. Yeah, so in general, all those methods, and there are a lot of methods that use PCA for that purpose, they have some limitations. Well, first of all, we have to say that PCA is a mature technique. We had that before, and it's really a mature technique, so really sound thing. So it always allows the construction of a broad range of similarity measures for local correlation of attributes. So it's really a good thing. Yeah, it can also be replaced by similar techniques like relevant components analysis, component analysis, independent component analysis, or any other thing that somehow rates or computes directions of variances, high and low variances, and can and the output can then be used to construct similarity measures. Yeah? But the key limitation is still alive. All approaches have typically this locality assumption, because PCA only works if the set of points on which PCA is performed is a fairly good approximation of the cluster, meaning that they really exist in the subspace or in the correlation, in the arbitrary oriented correlation, in the arbitrary oriented subspace we want to find for that cluster. Yeah. So if we have a lot of noise points in the local neighborhood, which is very likely in high dimensional feature spaces, so if we have those noise points, then PCA will be misguided. Yeah? So PCA has no chance to find the correct subspaces. And that is the key limitation of this locality assumption, that typically in the local neighborhood of points or cluster representatives, there are a lot of noise points in the full dimensional space, and so PCA will rather fail to detect the right subspaces. Not because PCA is bad, but just because PCA is applied to the wrong set of points. Yeah? So if we want to overcome the whole thing, we need a new principle to employ correlation clustering, and that is coming up on the remaining slides here.